Hi, my name's Jessica, and I'm a graduate student here at University of Wyoming. I'm going to try to talk, I've heard you guys read 7 brief lessons on physics, so I'm going to tell you a little bit about my research and how some of the stuff you guys read about relates to what I do, and just try to kind of connect some of it, show you guys some examples of what some of this might look like in what we're doing. So I study galaxies here at the University of Wyoming, so this one behind me is NGC 6946, or the fireworks galaxy. It's about 10 million light years away and is one of the closer galaxies I study. So this is right in our local neighborhood. But because it's so far away, I really need to be careful when I look at this that I take into account the fact that I need to use general relativity to understand how space-time might curve as light travels to us. And I know that this concept, in the book he describes it a little bit, but it can be a bit confusing. So I wanted to show you what this might look like. So what I have here is what I like to call the pink fabric of space-time. It's a nice flat thing at the moment. We don't have it, it's not curving yet because there's no mass. So it's flat. If I take my photons, little ping pong balls, and roll it across, it just goes like in a straight line. There's a little bit of sagging because my pink fabric of space-time is slightly old, but for the most part, no curvature, things move in a straight line. But if we take something massive, like what I have here, which is a 1 kilogram weight. There, maybe you can see it. I swear it's 1 kilogram. And I stick it into my pink fabric of space-time, it starts to curve. So this would be just like if you had a trampoline and you put a bowling ball in it. We get a potential well where the space-time is being pulled down by this massive object. So if we looked underneath, you can see again that this is a two-dimensional version of our three-dimensional curved space-time. And now again, when I take my photon and I roll it across, same exact thing I did, it's not going to follow a straight path. It's going to eventually, because of friction, fall into my massive object, my weight. But if I do it right, I might be able to get a nice little orbit, at least for a few times, as the ping pong ball, my photon, or other object, less massive object, rotates around my massive object. So this is exactly how the Earth is traveling around the sun, exactly how the moon is traveling around the Earth. Both the sun and the Earth create potential wells in the fabric of space-time, and the lighter object, either the Earth or the moon, is pulled around them. Now, fabric of space-time doesn't have friction, so we're not going to fall into the sun. We don't need to worry about that. This beautiful pink fabric of space-time, of course, does have friction, so it's a little bit more complicated. The really cool thing is that you guys are using this every day. Whether or not you realize it, you're using general relativity in your everyday life. Anytime you open Google Maps and it tells you where you currently are, it has to take into account that time travels differently as it comes in and out of the Earth's potential well. So as it bounces between your phone and the satellite that tells you where you are, it has to take into account that the time it takes depends on where it is in this potential well. So it's using the principles of general relativity to figure out exactly where you are on Earth. The other thing we can think about, we'll come back to the pink fabric of space-time. You guys also talked a lot about, or the book also talks about particles, and how quantization works in our universe. Sorry, I have to think about all the things I want to say, and all the things I want to show you guys. There's so many things. So if we come back to my galaxy, I've also got something here we call spectra. So this is if you've ever played with a prism, you notice if you take it and you look at this light, you can see a nice rainbow. We can do the same thing. I'll show you first, actually. Let me switch this to the sun spectra. So this would be sunlight. If you had a really nice prism, you could really bend this out. You could see that the sun isn't just a rainbow, it's got some dark lines. Those dark lines are there because elements in the sun's outer layers will block very specific kinds of light because they can only block certain energy because of the quantized nature of energy. So these different lines can tell us what types of elements are present in the sun's atmosphere. a really cool thing, this is how we actually initially discovered helium. So you might have noticed that the helium starts with helios, kind of that same similar Latin word for sun. So we've first noticed that some of these black lines didn't seem to match any element on Earth. There was no element that could produce the quantized energy levels that we were seeing in the sun. So we made up a new element and called it helium because it was only found on the sun. Later it was also found on Earth, but originally it was first found on the sun. So we can do the same thing with galaxies, which is what I was kind of hinting at earlier. Sorry, we're going to bounce back and forth here. We can spread out the light from galaxies. This is the light from NGC 6946 as a function of color, or wavelength, with redder, bluer being over here. This is blue, red being over here. And what we can see is there's different spikes, and those different spikes tell us what elements are present in that galaxy. If energy wasn't quantized, we couldn't use those spikes to figure out what these galaxies were made of, but because energy is quantized, we know that this galaxy has a lot of hydrogen. That's that 6563 is a big hydrogen line, so we can see that, and we can use that to figure out what exactly is happening in this galaxy. It's forming a lot of stars, so that line is really, really bright. It has a lot of baby stars that emit this line. Okay, so that's a little bit about curved space-time and a little bit about quantization. So those were the first two chapters of your book, General Relativity and the Quantized Nature of Energy, or Quantum Mechanics, how that relates into that. So the third chapter was about how we're learning a lot more about the cosmos, and we're just getting a better understanding of where we are in the universe. And what I really like about this chapter is it kind of points out that we're still figuring out where we are in the universe. Like, physics is not done. We still have a lot to learn, but we're going to keep working and we're going to keep trying to build a better understanding of where we are. And one of the ways we can do that is through your chapter 4, which was focused on the different types of particles. So I'm not a particle physicist, but I took a particle physics class in undergrad, and I really liked it. So I wanted to share with you guys some of what I learned in that class. So this, what I've drawn on the board, see if I can get this all in. Low-tech videos, is what we call the standard model of particle physics. Now it might look semi-similar to maybe the periodic table. That's kind of what physicists were hoping to find, was something that would be nice, elegant, and look like what we had found when we looked at elements, where we could actually predict where there might be a new element. We haven't quite got there with particle physics. These are our quarks up here. We have up, down, charm, strange, top, and bottom, and those pretty much make up everything that you guys interact with. They make up protons and neutrons, so the main stuff. There's also, of course, electrons you might have heard of, so these are our leptons, electrons, muons, and tauons. That's pretty much anything else you might have encountered. Every electron has a corresponding neutrino. These are almost massless particles that travel really fast and seem to show up a lot whenever anything changes from one type of particle to another, which is really important, and I'll talk about it in a second. Besides our quarks and our leptons, we also have bosons, which are force-carrying particles. So these allow things to interact with each other. So there's gravitons, photons, and then the W and Z bosons. So those are similar particles. Some of them have mass, some of them don't. Sorry, I was going to say they're all massless. That's not true. Some of them do. But these carry different forces. So these are how particles interact with each other. Finally, there are two other particles that we kind of don't know a ton about. The Higgs boson, which gives things mass, and we're pretty sure we've measured it, so that's exciting. Physics is growing. And then also the graviton, which would be what controls the gravitational force. But we haven't actually found that yet. It's a theoretical particle. So as physics continues to grow and expand, we want to keep adding to our standard model to better understand what's going on there. So hopefully eventually we'll have something similar to the periodic table of elements, but instead of elements, it'll be fundamental particles that can't be divided and help create the world that we live in. I wanted to show one other thing with this, one thing I really like. This is what we call a Feynman diagram. Sorry if everything's backwards. Sorry, low tech. But it shows something that's happening in the sun all the time. The sun produces energy through nuclear reactions, and those nuclear reactions are turning protons into neutrons, and a little bit of extra mass that gets lost in this process becomes energy. So what we see, oh, I kind of drew something wrong, that's okay. We start with 2 up quarks and a down quark, and then one of those up quarks decays into a down quark, and what we end up with is a neutron, decays with the help of the W boson, and we end up with some energy out, and that's how the sun is producing light. So understanding particle physics relates back to what we do in astronomy, because we need to understand how these particles change and interact in order to figure out how we produce light from stars, how galaxies glow the way they do. So it's really important for my research, even though much smaller scale. I like a lot bigger, shiny things. But the other thing I wanted to point out is that although our nice standard model, which is still behind me, is lovely, it's missing something, and it's a really big something that seems to make up about 70% of our universe. Nope. Sorry. Makes up about 23% of our universe, and that's dark matter. So 23% of our universe is dark matter, about 2% is the stuff on a board, and the other 70% is dark energy. And we can tell that there is dark matter by, again, going back to our pink fabric of space-time. So back over here, we have our, sun object, sort of, in the center. It's curving space-time. But let's kind of do a little bit of magic. We're going to grow everything, and we're going to pretend, instead of the sun, this is a galaxy. Now, we can figure out how many stars are in a galaxy based on how bright it is. But what we've noticed is space seems to curve more than we would expect. So the galaxies are too heavy for the numbers of stars they have. So there must be something else massive, and some other massive stuff around these galaxies that is curving space-time more than we might expect. So it looks like there's only 1 kilogram of weight because the other one's invisible, but we can look at how photons travel around it, and we notice that they curve around more than we would expect. We can use those curved paths of the photons to figure out how massive the galaxies are and compare that to the number of stars, and notice that we must have some other type of massive material in these galaxies that doesn't interact with light, we can't see, and that's what dark matter is. So there's this whole thing that we want to add to our standard model. We don't know how it fits in. We don't know what it is, but it's there, and it seems to be about, a quarter of our universe almost. So it's crazy, but we don't quite understand it. Black holes. He also talked a little bit about black holes. Black holes make these similar, incredibly deep, incredibly narrow wells in the curved space-time. And what I think is really cool is that one of the things that we've done fairly recently is we've been able to measure black holes colliding with each other through how it bends space-time far away. So there's a program called LIGO that does this, and I'm gonna stop this and turn the camera around so I can talk to you guys. Okay, I'm back. Sorry. So what LIGO does is it looks for fluctuations like ripples in space-time. So if we had our pink space-time fabric, if I could shake it because 2 things slammed into each other, that would be like the ripples in space-time that LIGO is detecting because black holes are slamming into each other in other galaxies. So we can detect this, we can actually measure lengths changing because of how black holes are interacting in other galaxies, which is mind-blowing. And that's what they're doing. There's one in Washington State, and there's one in Louisiana, and there's a few others, one in Europe, and they're thinking of building one in India as well. There's also talk about putting one in space, which would be really cool. And they look at very, very, very tiny changes in these 3-kilometer-long measuring sticks, essentially. And they use that to detect gravitational waves, which is something that Einstein predicted 100 years ago. So when he wrote the theory of general relativity, he said there should be ripples in space-time. 100 years later, we can finally actually measure them, which is awesome. We also measured the gravitational waves caused by 2 neutron stars colliding. which neutron stars are essentially stellar corpses. So if you have a really big star, when it runs out of fuel, it'll collapse, and if it's not quite big enough to be a black hole, it might turn into a neutron star, which is still really, really dense, but not quite like our singularity pulled down super, super dense thing that's like crazy. A neutron star is more like if you took the sun and you squished it down to the size of Laramie. So really, really, really dense, but not quite a black hole, which is like a single point that is as massive as the sun. And what we noticed when we looked at these neutron stars colliding is they're actually producing most of the gold in our universe. So if you have a gold ring, if you have earrings made of gold, if you, I don't know what else is made of gold, but if you ever held a piece of gold, there's a good chance that that gold was made when two neutron stars collided with each other, which is really cool. So two stars lived, exploded, died, left their corpses. Those two corpses slammed into each other so you could wear a gold ring, which is, like I said, is cool. We also might have heard the phrase, I love this, that we are all made of star stuff. This is essentially true. Stars are making carbon, they're making helium, they're making oxygen, they're making nitrogen. Most of those elements either come from the Big Bang, from the start of the universe, or they come from fusion inside of stars. So we are really made of star stuff, which is awesome. And that kind of brings me to where I wanted to end, which is that science is a really human process. So we come from the building blocks of the material. We're made up of all of those particles in our standard model, but we're trying to understand, and in the process, there might be mistakes, there might be things we have to go back and correct. There is still so much for us to learn, and we can use these principles of general relativity, of quantization, to really help us build a better understanding of our place in the universe. So that's kind of what I wanted to say, how what I'm doing relates to what you guys read about in the book. Hopefully this pink fabric of space-time example was slightly helpful. If you do have a trampoline, if you can like stretch out a sheet even over a couple chairs, you can kind of play with this idea yourself. We just have this one that's kind of built for this. It's a little stretchy, which also helps. But this kind of helps us visualize what we talk about when we talk about curved space-time, which is a really hard thing to visualize. And bringing time into it just makes it 10 times more confusing. If you do have other questions for me, please feel free to reach out. My name is Jessica Sutter. I'm a graduate student. I live in the building of physics, the physical science building in office 122. I can also be reached by email. My email is jsutter, S-U-T-T-E-R, 4@uyo.edu, and I love talking about this stuff. So I'd be happy to answer any other questions you have. I hope this video was semi-helpful and that you guys enjoyed reading about physics and where we are in the universe. Bye.